Okay, can be used to compute the static forces. Okay, what I mean that is, for example, in statics, when you are computing, when you're drawing a free body diagram and then computing the reaction forces, or the, in this case, we are not talking about static members, but more like there's a double pendulum or triple pendulum, it's in equilibrium, it's not moving because there is some torques holding that pendulum in place. We need to figure out what those forces are. Then Jacobian actually gives you those forces. It actually gives you the, it actually boils down to the momentum is what the Jacobian gives you. So let me first derive the expression and then the time, and then we just apply it on the double pendulum. So here's a bit of theory behind how do you use the Jacobian to do calculations. So assuming there is some body and it's subjected to forces. Now I'm drawing one, but assume there are n bodies, and there is torque 1, and if you want, you can put another body. Torque 2, say F2. So these Fs are forces, which are external forces, and you could also include things like its own weight, mg. And so let's assume that this body is in equilibrium. Okay, it doesn't move because the torques are compensating for the external forces. And we are interested in computing what the torques are given the forces. Compute taus given Fs. Okay, so we use a principle called virtual work. So what does virtual work is that assume that this force is F1, F2, lead this body to displace by a small distance, delta x. Now, delta x is a vector. It can move in the x and y direction. And that's not real. It's virtual work. It's not, it's imaginary, so to say. So that work can be quantified as F times dr, where this is displacement. Okay, again, we'll have f, x, and y components. This is the force. Okay, now for this to be meaningful, what we'll do is we'll always have these. So first of all, work is a scalar, right? It's a 1-by-1 matrix, so it's a scalar. So this force, what I have on the right side, should be a scalar. And we normally have delta in the 2D example is dx dy, so it's going to be a position. And let's assume that it is, we'll always assume that the lengths of these vectors are 2 cross 1. So it has 2 rows, 1 column, something like this, delta x, delta y, right? And so since all the forces are also 2 cross 1, fx, fy, that is, there's F1, F2, but they will have an X and Y component. For this multiplication to make sense, I need to take the transpose of F, because Fy, the way we've defined F is going to be 2 cross 1, but then when you take the transpose, you have 1 cross 2, and then when you take the multiplication, you get 1 cross 1. The other way of thinking of this is if you remember dot product, if the dot product is a scalar, so it's basically the dot product in this fashion. So that's the work done. That's the virtual work. We can also compute the work done due to the start. So again, just like there's a virtual displacement, the x and y direction, there's a virtual rotation in the θ1 and θ2 direction, where there are 2 degrees of freedom here. So we'll just write it as torque dot d theta. Again, the same logic, which is for this multiplication to hold sense, we need to tau transpose, because it's a 1 by n, just one here in this case 2 forces, but it could be n forces, n torques, sorry, and then corresponding to those torques will be n thetas. And so to make that consistent, we'll have always tau transpose and t theta, which is again a dot product. Now these works have to be equal to each other, because if they are not, then the system is going to have a net gain or change in energy, which means that it will move. So we'll equate the two. So we have net work is, let's call that dW, equals tau transpose d theta minus f transpose dr. And as I said, it should be 0 because there's no net motion. So then we have tau transpose d theta equals f transpose dr. We'll divide throughout by d theta. So we have tau transpose equals f transpose dr d theta. Okay, but what we have here is basically how the Cartesian coordinate, this is the Cartesian position, like dx dy, and this is the degrees of freedom. Right? We know that the rate of change of the Cartesian position of any point with respect to the degrees of freedom is nothing but the Jacobian. And so we can write this as this is equal to the Jacobian. And so we have tau transpose equals f transpose j. And then people normally don't write it that way because we have transposed on f. So just to make it in a more convenient fashion, we just take the transpose of the entire expression. So we need to take the transpose of both sides. Okay. So the transpose of transpose is just that particular matrix or vector. And the transpose of something which you've done in homework 1, if you have A times B transpose, that's the same as B transpose, A transpose. That's true for any A and B. So this can be written as J transpose, F transpose of transpose, which is F. So this is the expression we're after. It tells you you're given F, let's say that you're given this. You can compute the Jacobian, which we've done numerically or symbolically. We can then evaluate what the torque is. And this is the torque needed to keep that particular system in equilibrium. This is the static torque. Okay, so I'll show you how to do that for the same pendulum, double pendulum. A pendulum, if it'll have mass, so in order to stay at equilibrium, we need to supply some torques at the joint so that the pendulum doesn't move. And so we'll compute those torques. So this is the same figure as before. Just draw that again. Okay, two links. First link makes an angle of θ1. Second one makes an angle of θ2. Center of mass, G1, G2. I'm just going to call this E. Let's call this P. And then here, we don't have an external force per se. We just have gravity, M2G, M1G. And so if there are no torques at the joints, then clearly the pendulum will move like we've seen in the animation. But if we can compute the right torque at the joints, so torque, I quit that. Torque 1, torque 2, then we can keep this system in equilibrium. So our goal is to compute those torques. So compute τ1, τ2 such that the system is in equilibrium. Okay, so what we do is, now this is, first of all, you don't really need that expression to solve this problem. You can use your knowledge of statics, right? Draw a free body diagram first, your reaction forces, then do an equilibrium of forces in the x, y direction. So in this case, you have to do moment equilibrium in order to figure out those tau1 and tau2. That's one way to do it. This way, what I'm going to show you does not really require you to draw free body diagrams. It's just use that expression which I derived. So here we write torque equals J transpose times F. Okay, here are the torques. There are two torques, tau1, tau2. Okay, now remember there are two forces here. Those forces are acting at two different points. One of them acts at G1, one of them acts at G2. So we need to expand that expression for those 2 points. So the first force is at G1. So that's just, let me define the axis, X, Y. So the first force is in the Y direction or negative Y direction, so M1G. But then that should act with the Jacobian. You need to compute a Jacobian at G1. That's the first part. The second part is JG2 transpose 0 minus M2G. Okay. Remember that Jacobians are defined for an individual point. So the moment you have different forces at different points, you will have to use computer Jacobian of that point. Okay, so what remains to be done now is to just get the Jacobian at G1 and G2. Now, this is something I think I've done already over here. Okay, so this is JG1, right? I computed the velocity of G1 by using JG1, so that's already computed. And then right here, it's basically, so the Jacobian, I should have written it slightly differently. Let me put that. You can keep that. I'm just going to rearrange this so that it's already there in the form I wanted. Right, so this is how the Jacobian is. This is the Jacobian of G2. Okay, so I just need to take that, put it in this expression, and then I would have a formula for tau1 and tau2. Okay, so this is, let me just write it down the way I should have written it down earlier, that you have another reference to check it. So C1 cosine theta 1. Remember that there was C1 sine theta 1 write down, but you need to take the transpose of that. So C1 sine theta 1 will go up because that's the transpose, 0, 0, 0 minus M1G. And then the second line would be C2 cosine theta 1 plus theta 2 plus L cosine theta 1 C2 cosine theta 1 plus theta 2 C2 sine theta 1 plus theta 2 plus L sine theta 1 C2 sine theta 1 plus theta 2. Okay, so the last step is to simplify that. I'll skip that, but it's very obvious how to do that, right? Just multiply those two. If you want, you can just put it in Python and symbolic package to give you the answer. Note that I've taken the transpose. This is the transpose. This is JG2 transpose, and this is JG1 transpose. So the transpose has already been taken there. Okay, so when you look at JG1, don't get confused, it's the transpose. Okay, so that's the second application of the Jacobian. It gives you static forces. Okay, the third one is what we've done in the past, which is you can actually do inverse kinematics using the Jacobian. You don't need to do nonlinear root finding. We used fsolve in the past, which does computations for the manipulator inverse, right? We can do the same thing using Jacobians. We'll show you that, and then I'll show you how to do it numerically. Any questions?